All right, let's take a look at this scenario here. We have two blocks, and they're both initially at rest. And the one on top of the incline there is up at a height h on this incline. It's released from the top of the incline, slides down, and collides with block B. What we're told is that we can assume the first block changes direction after the collision. So it slides down, collides with B, and then bounces basically back up toward the incline there. What we're given is the fact that there's no friction, so we're not dealing with any frictional forces between the blocks and the surface beneath. So that's a simplifying factor in this problem. We're given the masses, we know h. We're also given the speed of the 2m block after the collision, and we're given the angle of incline, phi. So cool. And what we're asked to determine here is how far back up the incline the first block will slide after the collision. Okay, so we know we can apply conservation of momentum to the collision. You might be getting to the place now where as soon as you see collision, you're like, I know what to do. I apply conservation of momentum. But the problem here, I mean, the issue with that is that you can't apply conservation of momentum right at the beginning of this problem. If you think about it, right? Because both of the blocks are at rest. And can I say, like, if I release the block A, it's sliding down the incline. Is that a case where the sum of external forces are zero? No, it's totally not that case, right? It's gaining momentum as it slides down the incline. So sometimes students will say, like, wait, how can the momentum be changing? I thought momentum was conserved. And again, I'm going to remind you that when we talk about conservation of momentum, we're really talking about Newton's second law, right? So we're saying that the sum of the external forces on a body or system are equal to the change in momentum. Remember, this is an alternate statement. I've gone over this before of Newton's second law. So the only time that we can really say the change in momentum is zero is if we can make the argument that the external forces are zero. And that has to do with how we define our system and such. So let's take a look at that for here and let's say, let's define our system as the system of two blocks, right? So blocks A and block B. So at the very beginning, we can't use momentum analysis on this scenario because block A obviously has an external force as it accelerates down the incline. What we can do is we can apply energy analysis though. So let's not forget about that. Remember that we usually use energy analysis to analyze a process, and we usually use momentum analysis to analyze an event. And that event usually, typically, takes place over a very short amount of time. It is typically a collision or explosion. In this case, we have a collision. So we will use momentum analysis, but we will use it as applied to the collision only. So pre-collision, we're going to apply energy analysis here to the block sliding down. So this is the sliding of block A here. That's what we're applying it to. Okay, great. So what we're going to look at is the change in overall energy, right? Mechanical energy equals to the work done by non-conservative forces. And if I look at that block A, I consider I can consider a free body diagram for block A while it's on the incline, right? While it's on the incline. So think about what that's going to look like. Oh, yeah, sure. There's a normal force on that block, right? And then we have the weight of this block. Block A is mass M, and we know that angle. And that's it. There's no friction at the interface. There's nothing else touching this block, right? So the only non-conservative force is normal force. And because my displacement is at 90 degrees from normal force, there are actually zero works here done by non-conservative forces. So my final energy for block A is going to be the kinetic energy when it's at the bottom of the ramp, right? 1/2 m, I'll call this V sub A squared. My initial energy for this block is, of course, the gravitational potential energy it has upon release, mgh. Conveniently, we're given h. And the works done by friction, or I'm sorry, works done by any non-conservative forces are zero here. So that's nice. It allows me to get a nice little expression for V sub A, and that is the speed of block A once it has descended the incline root to GH. Okay, so that's the square root. Got it. Now we know how fast block A was approaching block B, right? So now let's do our momentum analysis here. I'm going to switch colors for that. Now let's do our momentum analysis. And for this, I'm going to pause and actually draw a little bit of a diagram real quick. So for this momentum, it's the collision that we're interested in, right? So I want to look really quickly at the before and after for the collision. So the before case, what's happening in the before case? Well, block B is just sitting here, right? And block A is approaching it there at VA, which we just found, right? So block A is approaching block B, and block B is at rest. Okay, and then the collision happens, right? You have your collision, boom, boom, collision. So after the collision, what's going on? Well, now block B is taking off this way, right? I'll call this VB prime. And block A, the problem statement told us that, assume the first block changes direction after the collision. Block A is taking off to the left, and I'm going to call that VA prime. So I've got two different directions to keep track of. Momentum is a vector. I need a sign convention. I'm going to say rightward positive here. So in your momentum work, be sure that you always choose and stick with the sign convention, or things get really weird really fast if you just are pretending everything's in the same direction when it's not. Okay, so now we can write our equations for this. If I look at initially, where's my momentum initially here? It's all in block A traveling to the right at VA. So block A has a mass m, and then the velocity here is V sub A. It's to the right, so it's positive. And after my final momentum, now I have momentum in either block, right? In both blocks, they both have some. So I'll start with the positive one, which is rightward, which is block B. It has a mass 2m, and its speed after the collision is VB prime. It's positive because it's to the right. And then VA, my block A is heading off to the left, which is negative mass m and VA prime. So when I'm doing momentum problems, I'll usually prime the after and not prime the before, just as a way to keep things organized. So now we can ask ourselves, like, are the sum of external forces zero? Yeah, I mean, we have gravitational force down and normal force up supporting the blocks, right? There are no other forces, those sum to zero. And then the only other forces on the blocks are the forces they exert on each other, right? So all kinds of forces they're exerting on each other in the collision. But remember how we define the system. We define the system as a system of both blocks. So those are internal forces. That is key. It's really, really important because all those messy forces, the collision forces, are internal forces. So I can make my case for sum of external forces being zero. And that's what allows me to set the initial and final momenta equal to each other. So I can set initial equal to final momentum. And then when I solve for VA here, I can solve for VA and get 2 VB prime minus VA prime. Okay. So that just gives me another equation there. I know that I want to solve for VA prime, right? I can do that. And remembering that I have already an expression for VA that I did in the first part in my energy analysis part in terms of givens. So then I actually can solve this for this VA prime. And that's going to end up being 2 VB prime minus root 2GH. Okay. And remember that VB prime is one of my givens. Cool. But really, what this problem is asking me is how far back up the incline the first block will slide. I just got something really important though, and that is like how fast is it going as it approaches the incline? And remember that there's no friction. So now I can apply energy analysis um, using this speed right here, right? Knowing that it's going up the incline at that speed, I can use energy analysis to figure out how far up the incline it goes. And because that's review at this point, I'm just going to leave that part to you.